let's look at this. If you have a pen like this pen will have one reaction in the AX and one reaction in the AY. If you have a ruler like this, a ruler B, so there is only one reaction in the Y. If you have a fixed joint like this, so it will be looking like it's attached to the wall. So you'll have CY, this is C, CX, and then a moment. So a hinge will have two reactions, a ruler will have one reaction in the Y, and a fixed connection like this, CXCY, and there's a moment C. If you have a uniform distributed loading like this, 100 kilonewton per meter, and the distance is 5 meters. So to find out the equivalent loading is 100 times 5. So it's 500 down. So 500 down, 500 kilonewton down, and also it's in the middle. Since this is like a rectangular, so 2.5, 2.5. It's in the middle of this loading. If you have a triangle loading like this, 100 kilonewton per meter and 5 meters like this, triangle loading. So the way we do it is by applying the method 1/2 times 100 times 500. 1/2 times 100 times 500, that's 1/2 times 150, 50 times 5, 250. So the loading is 250. Okay, then where is the loading, the distance or displacement, or the location of this loading? So this loading, we know it's 250 kilonewton. The location of this loading is 1/3 the pace, 1/3 the 5. So 1/3 the 5 is 5/3. So it's here, 5/3. Okay? And the other loading is 2/3 of the distance of 5. So 2/3 of 5 is 10/3. So the distance from here to here, the equivalent loading from this location and this, is 5/3 and 10/3 the other loading. To draw a shear moment diagram, let's say that if we have a very simple beam like this, 50 kilonewton going up and 100 kilonewton. Let's say that these are the reactions. How could you draw it? When you start with the shear, you have to put V, Kn, and you have to put, this is the V means shear. Kn is here loading, Kn, kilonewton. And X, the distance, is in meters, so you put X meters. So you have to put it like this. V Kn, this is to make sure that this is the y-axis are all in kilonewton, and the distance in the x-direction is in meters. Okay, in the shear, we only deals with the y-axis forces, not the x-axis, not the moments, only the shear in the x-axis y. So at this point, you can see that there is a shear up 50, that's plus, and here there is no loading, so it will be uniform shear, and then here 100, and it's going down, so 50 minus 100, so 50, so if you go uniform, it will be 50 here, minus 100, so it's going to be minus 50. No loading, so it's uniform, and then plus 50, so minus 50, minus 50, plus 50 is 0. In order to find the moment, you have to find the area under the shear. So this is 50 and this is 2, so this is 100. 50 times 2, 100 kilonewton meter. So this is 100 kilonewton meter. And this is minus 50 times 2, that is another minus 100 kilonewton per meter. Kilonewton dot meter. So we have the area this in the positive, and we have the area this here in the negative. If you have a shear in the 0 here, which means that there's a change of moment. So let's start the moment. The moment is kilonewton meter. Kilonewton meter, and here it should be X. You should make it also put here X meter. We should start here from moment 0. Moment 0 here. There's no moment here, so we should start from 0. Okay. Here, if you go, as we said, the area was 100 kilonewton meters, so you go 0 plus the area is plus 100, so 100, and since this is uniform, you will have linear moment. Okay, plus 100, and here plus the area, the next area it is minus 100, so plus 100 minus 100 is 0. And it is linear because this is uniform. Uniform shear will give you linear moment. Okay?